Hello again. Thanks for joining us on another episode of Space Nuts. My name is Andrew Dunkley. It's great to have your company. I hope you're well. Coming up in this episode, some exciting stories, and one of them is a new CSIRO map developed in Australia of magnetic fields. Now, it's been quite a while since they updated this, and they've got a new one out, and it's quite extraordinary, the way it was done and what it shows and what it can be used for. We've also got a new report about the relationship, or otherwise, between black holes and dark matter. Now, this is interesting because it's only been a theory until now. Now, this isn't absolute proof, but it's a step closer to proving there is something going on between the two of them, and they just don't want anyone to know. And the world's first trillionaire goes public. We'll talk about all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he's with us again for another dose of whatever it is he takes before he talks to me. It's Professor Fred Watson, astronomer at large. Hello, Fred.
It's a good cup of tea that I take normally.
I've been drinking a bit more tea of late, only because by the afternoon I'm not really into coffee, but today I did have coffee, so do love my coffee.
I do too, but... Yeah.
I make my own. I got the whole barista thing going. I'm even doing latte art, Fred.
Oh, really?
Yeah,
Can you do
I don't know
those?
if you'll see this. I took this photo today of my latte art. Can you see that?
That is brilliant.
Yeah.
Whoa, that's real pro
Self-taught.
stuff. Self-taught
Self-taught.
barista.
Yeah. I don't know what it is.
It looks like
some kind of flower, like a lotus flower.
Well,
or
it
something.
reminds me of ears of corn.
Oh, yeah, it does, doesn't it?
Yeah.
That's
what it
yeah,
reminds
or
me
just
of.
ducks
So
sitting on top of each other or something.
Could be your corny latte.
Yes, it could be. Yeah. Anyway, I've been working on that. That's
Very good.
I'm
impressed.
I was going to do a whole series and put them on Instagram of my progression through being really crap at it and to reaching a point where it's, something to look at, but I didn't bother, and now I wish I had because I've had some epic fails, but that one came out quite well today.
That's very nice. Well done.
Right, let's get on with this because we've got a lot to talk about as always, and our first story comes from Australia, mate, and it is the remapping of the magnetic fields of a large swathe of the universe, or is it a large swathe of whatever piece of the backyard sky someone can see out of? I'm not sure how much of it they got.
A good chunk of it, actually.
I thought so.
Because so these observations were made at a site in Western Australia known as Inyarimana Ilgari Bundara, which is Wadri for sharing sky and stars. The Wadri people are the traditional owners there. And it's also called the CSIRO Murchison Radio Astronomy Observatory, but we tend to refer to it as Inyarimana Ilgari Bundara because it's a very nice name.
Yes.
So what's there? There is, first of all, it's the site for the low-frequency arm of the Square Kilometre Array. The Square Kilometre Array Observatory exists in three places. One is Western Australia, where the low-frequency antennas are. The other is in South Africa, where the mid-frequency antennas are. And the other is near Manchester, where the headquarters are. That's Jodrell Bank is where the headquarters of SKAO are. And they've just got a new director, General, by the way. Jessica Dempsey, I think, is her name. Somebody I've kind of run into before over the years, is the new Director General of the SKA Observatory. Anyway, also on the site in Western Australia is ASCAP, which is the Australian SKA Pathfinder, ASKAP.
By coincidence, an ASCAP is also something you can wear if you don't have any pants.
There's no answer to that, Andrew.
No, that one. We just let that one
No,
hang.
I might leave that one alone. Yeah. Anyway, notwithstanding that, see, you don't get this on other podcasts, do you? It's why we're number one in Iceland.
That's right. We are. Thank you, Iceland.
Absolutely. Go for it. I forgot. Yes, ASCAP, not the garment, but the radio telescope array. 36 12-meter dishes, which were built over I guess 15 years ago was when they started. It's been operational for probably more than 10 years now and done some fabulous work. But the latest piece of high-profile research that's come from ASCAP is, exactly as you've said, the largest magnetic map of the universe ever produced, 5 times larger than all previous efforts combined, and it marks the beginning of a new generation of research into the field of intergalactic magnetism. And I'm reading there from the CSIRO news release. You could probably spot the hype, but it's well-deserved hype as well, and well-deserved kudos to the team leader, Alec Thompson of CSIRO. What they've done is used the telescope in a I suppose an innovative way. How do you measure magnetic fields? Well, you know, normally to measure a magnetic field, we stick a magnetometer in the way. That's how magnetic fields are measured in the solar system by various spacecraft, because they carry magnetometers, which measure the local magnetic field of where you are. And that gives us some insights into not just the sun's magnetic field, not the Earth's magnetic field and the sun's magnetic field, but also, courtesy of Voyager, the 2 Voyager spacecraft, the galaxy's magnetic field, because we can sense the direction of that with the magnetometers carried by those spacecraft, which are now beyond the sun's magnetic influence. But it's quite a long jump from the environs of the solar system to the universe as a whole, which is what these scientists have done. And the basic technique is it's all about polarization. And we've talked about polarization before. We all know what it does when we wear our polarizing sunglasses and you're driving your car into the sunlight and there's a huge reflection coming off the road, especially if it's wet, and your polarizing sunglasses magically take that away. Yeah. That's happening because the light waves have they're, if you think of them as just being wiggles in space, which they are, electromagnetic wiggles, they have a preferred direction. Normal light has a mix of all these directions, but it turns out that you can separate out them by using, well, a polarizing filter, which is what we've got in our sunglasses, that only lets through the vibrations that are vertical. That's the vertical direction of the light that's coming to you, because the horizontal ones, which are very much reflected in the reflection from the wet road, they are cancelled out, and so you don't see them. So we're kind of familiar with that that idea of the direction of vibration of light waves. Well, the same holds good in radio waves. And so ASCAP and many other radio telescopes can actually sense the polarization of the radio signals that they're receiving from deep space. And so that's all well and good. You can sense the polarization, but you can also detect if that polarization's been twisted. And that's what happens when the light passes through a magnetic field. It actually rotates, called Faraday rotation. It's the plane of the radio waves twists, and you can detect that with an array like ASCAP, and that is what has allowed people to measure the magnetic field of the universe, because what you do is you look at the light from a distant galaxy and you look at the way its polarization changes as that light comes towards us, by using this technique. And so what you're saying is that you've got a kind of, a beacon lamp in the distance, and what you can sense is what's happening to the light coming from that as it passes through magnetic fields on its way. And so that's the basis of the map. As far as I can tell from, because I'm not a radio astronomer, which is patently obvious probably from the way I'm talking about it, I think you probably don't know how far away that magnetic field is. And so what you can infer is how, for example, how rapidly it changes depending on the position in the sky. There's when you look at this map, and I urge our listeners to have a look at it, it's pretty easy to find, the largest magnetic map of the universe yet. You'll see lots of colours. The colours, I think, are colour-coded in that, I think, if I remember rightly, red is with the North Pole pointing towards us of the magnetism, and blue is it pointing the other way. And so that lets you sense the magnetism along that line of sight. And so the biggest detail is actually in the galactic centre, which is full of churning magnetic fields. I guess you're having a look at it now.
I'm looking at it right this minute, and you're right. That they're explaining that just like you've got blue shift and red shift with light waves, the magnetic fields have the same kind of qualities in terms of north-south on the magnetic plane. And yes, the centre of the Milky Way galaxy is probably the most volatile part of this entire picture. Which is not surprising. We live there. We know.
That's right.
We know all about volatility.
Yeah. It's home from home. And just going back to what you said a few minutes ago, there is a hole in the map, and that's because ASCAP, there's certainly regions of the northern sky that ASCAP can't see because they're permanently below the horizon. They're relatively small, actually, because ASCAP can look a long way down towards the horizon, much further than we can in optical astronomy. In optical astronomy, the atmosphere just gets too thick when you're looking very low down, and so you get all the distortions and everything from the atmosphere. That doesn't happen with low-frequency radio waves. So the gap that's missing because of the northern hemisphere, because it's not visible to the telescope, that's actually relatively small compared with if it was an optical astronomy picture that you were looking at. But yes, this map has the line of the Milky Way across its equator, across the middle. Lots of magnetic turbulence in there. Some really intriguing features, things that look like magnetic fingers just sort of pointing around. It's a remarkable map, which I encourage people to have a look at.
Now, just by way of taking this a step further, what can they now, or what can anybody now do with a map like this? Because it's been made publicly available, hasn't it?
Yeah, so that's exactly right. Those data are now publicly available. By the way, I do like the name of it, which is SpaceX. Yeah. So RAX is the Rapid ASCAP Continuum Survey. And I've forgotten what SPICE is, but it's something equally delightful. But the SpaceX survey, I think, is it's got its own charm about it.
I was going to say something tongue-in-cheek about a girl group named something to do with spice.
Oh, yes, I know the one you mean.
Then I thought, no, you can't really associate that with racks. You could get yourself smacked across the face.
No, I would leave that well alone.
I will. I won't mention it.
Yeah. So as you said, the data are already publicly available. Research groups are already actually digging through this to see what it tells us about the magnetism of galaxies for a start. It's and just the way the environment of a galaxy is dominated by a particular magnetic field. It's only recently that we've understood that cosmic magnetic fields, i.e. magnetic fields in space, play a huge role in so many areas of astrophysics, but certainly in the way galaxies evolve over the billion, I suppose they are. The way they evolve is very much dominated by the local magnetic fields. And one of the big puzzles in cosmology, the science of the universe as a whole, is where did these magnetic fields come from in the first place?
Yeah,
and it's actually one of the things on the list of target science that the square kilometre array itself was designed to address. What's the origin of the cosmic magnetic field? Because we really don't know how they came to exist, and more than that, we don't know how magnetic fields have changed as the universe itself has evolved. All this lets you do that because, of course, as you look further out into space, you're looking further back in time. So there's a time dimension of this as well.
Yeah, there's a lot of magnetism out there, and as you say, they don't know where it came from. We probably would have solved it, except dark matter and dark energy came along, and we went, "Oh, well, this is more exciting." But it's just another one of those mysteries. By the look of it
is, and I'm sure all the scientists who've been involved with this have got magnetic personalities.
Oh,
sorry, I do my best. We aim to please.
Pretty good, that one. All right. If you'd like to read up on it, you can do that through the CSIRO website. It's an Australian website, and you can download the map. It's only 6 million megabytes. 6 megabytes. It's not a big file in the modern age.
No.
You can also read the paper in publications of the Astronomical Society of Australia. This is Space Nuts with Professor Fred Watson and Andrew Dunkley.
0G, and I feel fine.
Space Nuts.
All right. Now,
you did press record, didn't you?
I did press record. Yes. Yes. The giant gap was a misfire.
Oh, good. That's good. Okay.
We get those. Now, our next story, it's a new report about the relationship between black holes and dark matter. Now, this is something that our audience has quite often thrown up. There's got to be a connection between black holes and dark matter, et cetera, and now they've released a paper that's suggesting just that.
Yes, this is really interesting stuff, and of course it covers two of the most popular topics that we discuss on Space Nuts. This is research from Virginia Tech in the United States, and it's very neat because it uses a technique that I've always found absolutely fascinating, which is, it's got a fancy name called reverberation mapping. But we usually talk about light echoes. And the easiest way to envisage it is the one that I think drew everybody's attention to this phenomenon back in the 1980s. When supernova 1987A, the nearest supernova to us since Kepler's supernova in 1604, I think it was, that became very much the object of attention. It was in the Large Magellanic Cloud, so 165,000 light years away from us as the crow flies. And what was discovered as time went on was the supernova explodes. You've got this brilliant flash of light. It was easily visible to the naked eye. I remember looking at it. And then as time goes by, the light fades. But what you get as time goes on is a series of rings around the site of the explosion. And those rings are caused by light being reflected off clouds of dust, which are between us and the supernova. And you can do all kinds of really neat calculations to discover how thick those clouds of dust are, where they are in relation to the supernova. One of my colleagues, now sadly no longer with us, David Allen, was a past master about working on this and writing about it. And those rings are called light echoes because it's the echo of the light of the supernova, which has now faded away, but you can still see it because it's bouncing off clouds of dust in space. So what this article is about, the Virginia Tech work that we've just mentioned, is we know that black holes, supermassive black holes, are surrounded by swirling disks of matter. They're called the accretion disk. It's the stuff that's basically swirling around the plug hole before it either gets sucked into the black hole or shot out vertically from the poles of the black hole, the rotation poles, in the form of these jets, which we hear a lot about. But the accretion disk itself is bright, and it in X-rays and radiation. Once in a while, a larger dollop of matter enters the accretion disk, and you get this outburst. You get a brilliant outburst of radiation, and that outburst is relatively short-lived. It might last for a few weeks or even months, but it's short-lived. And so what you can look for is a light echo around it, because that light radiates outwards from the accretion disk, and if it hits anything outside it, it will reflect back to us, and we'll see it at a later date from when the bright event itself happened. So you see the bright event in the accretion disk, and then at some time later, you see an echo of that light, which is being reflected off usually gas and dust, which is surrounding the accretion disk. What this story is all about, though, is that when you do calculations about how much material there is in the accretion disk where the echo is taking place, you get a much higher mass than what you can see. And that's also always the kind of telltale signature of dark matter, when you can only see a limited amount of stuff, but gravity tells you there's much more there.
There's more there.
And that's exactly the basis of this story. So it's just a new way of detecting the dark matter around black holes. But it looks as though black holes, as you'd expect, not only are a magnet for regular matter, a gravitational magnet, I guess it's not magnetic in the sense that we've just been talking about, but a gravitational pull for normal matter. It's also a gravitational pull for dark matter as well. And it looks as though the dark matter actually congregates around black holes, that we've got these build-ups of dark matter in the vicinity of a black hole. Quite remarkable.
Now, the situation is that they haven't absolutely proven it. They've just come up with a way of suggesting that this might be the case, but it's not absolute. It's not fact yet.
It is in the sense that they've looked at this for 14 different galaxies, and all found cases where what you're looking for is the way the mass changes with distance from the black hole. And that mass is increasing because you're looking at stuff swirling around. But the increase in mass is faster than the visible matter on its own can explain. Yeah. And that's it's a kind of smoking gun for dark matter, really.
Yeah, I've found the paragraph. It says data limitations mean the results are a proof of concept, not a definitive detection, but the study outlines a clear path to confirmation.
That's right, yeah. So
we're almost there.
We're almost there. That's exactly right. We're almost there.
That is very exciting news, and that will stop probably 75% of the questions we get on our Q&A editions.
Well, it might, but I bet it produces another 150% about what it is that we're finding and how do we know, and why isn't it Mond and things like that.
Yeah. Yes. Oh gosh, it'll never end. It will never end. I hope it never ends. I think it's great.
So do I.
But if you want to read about it, it's at phys.org. They published the paper in the Physical Review D. Does that mean there's an A, B, and C that comes before?
Yes, it does.
I assume so, yes.
But that's a high-profile journal, though, Physical Review. It's definitely, it's ranks with Nature and Science and these very high-profile journals. So it's not work that is in any way second-rate. It's not like Space Nuts where it's adequate. This is top-rank stuff.
Indeed it is. So read about it at Physical Review or at phys.org. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Our final story, Fred, takes us into the realm of publicly offering your company up on the stock exchange.
I wonder why we're going to talk about that.
I wonder why. The world's first trillionaire has just done that in a very interesting way, and to coincide with the launch, he's selling stuff like we do on the Space Nuts shop, all sorts of little bits and bobs if you want a piece of the action.
Yes, the IPO merch.
It really is a remarkable story, though, Elon Musk and SpaceX, because as this article briefly mentions, he didn't think the company would survive. No. He didn't expect it to actually be a success. He gave it a very low chance of lasting. And look at him now.
Quite so, the world's first
trillionaire.
Yeah. It's I mean, I don't honestly. I know virtually nothing about the world of high finance,
Well, you know more than me then.
When I see numbers like millions and billions, I always expect there to be light years after them rather than dollars. But yeah, it's the public, the IPO, initial public offering, has valued this company at something absolutely huge compared with all the other tech companies that are being floated or are likely to be floated into public ownership. It's enormous. Is it 170 billion? Am I thinking of the right number there? Or is that light years? That could be light years.
I don't know.
Anyway, the bottom line. So yes, that was over the weekend that offering IPO happened, and it was very successful. I heard people on Friday saying, "Oh no, it'll probably just fail because nobody will actually believe what Elon Musk's saying."
Yeah.
Well, they might not have believed what he was saying, but they put their money where their mouths were, and so it's done very, very well. I think the number I'm thinking of is $160.95, which is the share price.
Well, I've just looked it up now, and I know this is being recorded, so by the time people hear this, the number will change. But at the moment, at this very moment, $192.50 in US dollars.
All right. So they've already gone up then.
They've gone up 19.6%.
Yeah.
In fact, they're up 31.55% today.
So not a bad investment, really, if you're into that kind of thing.
Yeah.
Well, we're not into that kind of thing, but we're definitely into merge. And that's what this story's about.
That's right.
Because I guess the one thing you can not accuse Elon Musk of is lacking flair, because he's done this very nicely. You can buy a mission patch for the IPO, which says the future is public. There's a lovely embroidered starship in the background. In the middle, it says SPCX, which is SpaceX. Lift off underneath it, and SpaceX 2026. And it's also got a four-leaf clover on it, which I think is present on all Elon Musk's SpaceX.
I think that's been his logo since day one.
Yes, yeah. A sign of good luck. Maybe that's what's done it. But the thing I liked was you can have a souvenir bell. And I guess, I don't know whether bells are normally associated. I know they're certainly associated with the stock exchange, but whether with public offerings they're associated, but they certainly are in this case. And what he's chosen for the shape of his bell is something absolutely perfect. It's the bell of a Raptor engine. These rocket motors have a very strongly bell-shaped thrust chamber. I guess it's the opening that lets all the gas out after it's been ignited in the combustion chamber above it. And so it's a scale replica of the Raptor engines that actually power the Falcon Heavy, the Super Heavy booster, which is the basis of Starship. It's got 33 of these, and this one's got a little clapper in the middle that lets you ring it, as well as all the pipe work. And apparently it rings, yes, because there's a video on the website that shows you that.
Yeah. They haven't released those yet to the public.
That's right.
They will be out probably, I think they're talking December.
Yeah.
They're sort of an 18 centimetre or 7-inch scale model of the SpaceX Raptor Bell. But this one has a clunker in it that makes it ring. I don't know what that thing's called inside the bell. The dingy thing.
Clapper. It's a clapper.
Is it?
That's the technical name, for
anyway. So they're selling those. They're selling tote bags and, as you said, mission patches, T-shirts, caps. Don't let it. He's the sort of bloke that never lets opportunity get away.
None whatsoever. I did hear some of the things that he said publicly at the launch, which made me cringe, because I can just about believe that we might get humans to Mars in his lifetime. It won't be millions, and that's because that's immoral, apart from anything else. But he was talking about flying around the solar system and beyond. And at the moment, that is off the agenda. Just physics doesn't let you do that.
No.
And just actually as a little footnote to that, I read a paper yesterday, which is about, the idea of using photonic propulsion or basically light energy blasted at a light sail. You've got a laser, you fire it at this light sail and the spacecraft accelerates because of that. That's all fine and dandy and will work if you can make your spacecraft light enough. But it turns out that you're not ever going to get near the speed of light. You beyond about 75% of the speed of light, you get something called relativistic drag, where space itself drags on the light sail, as well as any kind of interstellar matter that you've got to plough through at the 75% of the speed of light. So that's not going to get us touring around the galaxy.
No, we'll have to find another way.
Need another way, yes.
They need to go to science fiction writers and see what they've come up with.
Maybe that's what Elon's thinking of. Maybe he was suddenly in the realm of science fiction, but he didn't bother to tell us.
No, maybe not. No, but there's nothing fictional about his IP.
No, not at all. Not at all.
Initial public offering that is out there, and it is going gangbusters. It's burning like a raptor at the moment.
Yeah, probably will. I mean, you've got to give the guy credit. Two of the biggest breakthroughs of our generation, electric vehicles and reusable booster rockets, and basically they've come from him.
Yes,
certainly with Tesla.
Yes, they have. It's quite extraordinary.
Yep.
You can read about it at collectspace.com. We won't tell you all the prices of everything he's selling because it's you go and have a look. It's totally your call. But I do like the idea of mission patches, and I'm pretty sure I suggested that to Hugh many years ago that we should have mission patches. Yes.
We need yes, we do.
Yes,
I
thought
some,
we should. A new one for every episode.
Oh, all right, okay.
No, that's a bit much.
Look, the trouble is the mission patches, they would just be adequate. And if you
they would. Although I think our logo would make a great patch all on its own.
Yeah.
Anyway, we'll do that one day maybe. I don't know. There's plenty of other stuff in the shop. Just go and have a look in our shop. It's on our website, spacenutspodcast.com or spacenuts.io. Click on the shop link and buy yourself a pair of socks, or a notebook, or a coffee cup, or a hat, or a hoodie. Stickers. There's just all this great stuff there. I've got some of it. Look, I've got my cup here. See, here's my cup.
Oh, that's nice.
A Space Nuts cup.
I might have one of those somewhere.
You probably do, yes. And I've got the tote bag as well.
Very
so
good.
we thought of that before Elon. He's probably using the same company that we do.
No.
But yes. I think that brings us to the end. Fred, thank you so much.
A pleasure, Andrew. Good to talk, and we'll speak again soon.
We will indeed. Professor Fred Watson, astronomer at large. And thanks to Hugh in the studio. Couldn't be with us today because he wants to be the world's second trillionaire. And he's just put down $5 and he's just watching to see what happens. And from me, Andrew Dunkley, thanks for your company. We'll see you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.